All right, so as I'd mentioned, uh, I was going to put together this bonus lecture. I've answered all these questions on Piazza or Alston or Josh have um, on Piazza, but I thought I'd make a really quick video just because it'll help you with your project moving forward with your project, especially now that you're getting into the fatigue analysis in your project. Okay, so enough of that. Let's play here. All right, so bonus questions, bonus comments based on. Why don't you play here? PowerPoint. Um, bonus comments based on Piazza questions. All right, first of all, load factor versus gradient factor. As we've talked about, I don't particularly agree with the way our book deals with this, and here's why. So if you look at where's my stylus isn't plugged in. That sucks. All right, so there's a wasted 30 seconds of my video. I don't particularly agree with the way our book deals with this stuff. Primarily because if you look at the load factor, it's one for bending and axial, and the torsion is different, right? This one is different. But then for the gradient factor, right, it depends on the size and the loading, right? So this doesn't make more sense. Remember, the reason for both of these have to do with the volume of material exposed to stress. Right, so that's the whole point of this. So what we will do, and this is all in the roadmap, we're going to say for axial loading, we're going to give this a factor of 0.85. Now that begs the question, well, what if you have axial and bending? What do you use? Well, you have to figure out some way to combine those, or determine which is the dominant one. In your project, there is no dominant, there is no axial loading, right? So you can focus on this. But in general, you should say that if you're dominated by axial, use 0.85. If you're dominated by bending, use 1.0. All right, so you have to decide, and if it's somewhere in between, then interpolate, right? And then so for the gradient factor, so we're going to make this a 1, right? Why is that? Because we've already accounted for the 0.85 in the loading factor, right? And why does it get bigger? Because the probability of finding an imperfection, the probability of some grain boundary being exposed to a high stress is greater the bigger the shaft is, right? Okay, so and the rest of this, I think we're good. All right, so next one, distortion energy and other equivalent normal stresses, right? So we need to compare apples to apples. Compare apples to apples, right? Which means when we're comparing mean and alternating stresses, we want to compare to our Moore test, right? Which is sigma, right? That's a normal stress. So we need to take shear stresses or stress. Right, we need to take shear stresses and convert them somehow to normal stresses, right? And there's two ways to do that. One is to use the Moore circle, where we have sigma and tau, and then we make a Moore circle that looks like this, and then I can come up with an equivalent normal stress or maximum shear stress or something like that. Alternatively, I can use distortion energy, which is sigma prime or sigma equivalent, and that equals, I guess I can't write very fast in PowerPoint, sigma squared plus 3 tau squared, right, square root of that. So this allows us to compare normal stresses, and that's what our Moore fatigue test is based on, is bending and normal stress. All right, and which also is the reason that for bending, you know, for bending here, I'll draw a picture of this quick. Whoop, go back here. I don't know how that happened. For bending, remember, if this is a circular shaft, you know, the stress is highest at the outside and goes down to 0 in the middle, right? So it's already asymmetric, and that's why the strength actually goes down for axial, right? Okay, anyway, that's that. We've talked about that. Equivalent, mean, and alternating stresses. Different sources disagree, right? So for the mean stress, right, it could be you know, principal stress, could be normal stress. I guess the principal stress is a normal stress. Could be distortion energy, right? And then for the sigma alternating, same thing. Could be a principal stress, could be a normal stress, could be a distortion energy. Most books, most references use distortion energy for the alternating stress. That's the most common, right? But you check 10 different sources and you'll find at least 3 different ways to do this. Okay, and then that's just welcome to engineering. Again, if something fails, be prepared to justify your decisions. Okay, then finally, Goodman and ultimate shear strength. You know, someone said for pure torsion, what is SUT? Right, and that's a great question. So we can write the ultimate shear strength, right? Ultimate shear strength, ultimate shear, is somewhere between, let's call it 0.67 SUT and 0.8 SUT. Now, that's not a very not a very satisfying answer, is it? Well, get used to it. This is engineering. So, yeah, good question. But the final comment is that that's not a very good question. Because if I'm going to draw a Goodman diagram, right, what are my axes here? Sigma mean, sigma alternating, right? And then I have some point here, right, which is sigma comma sigma, right? I don't use Goodman. Goodman is no good for shear stresses, right? It's good for normal stresses, which is why we have to figure out, you know, mean and alternating stresses. Normal stresses. We're interested in normal stresses. The Goodman diagram is only good for normal stresses. Okay, 8 minutes. I make fun of this one. I mean, this is actually a really good question, but it doesn't apply. For fatigue, we talk about normal stresses. Right, that's why you know, we have this 0.58 in torsion, right? Because that's 1 over the square root of 3. So, okay, that should, as you start the fatigue analysis on your project, you guys should be all set.